Hello, my name is Andy Yaming. My matrix number is 07DKA20F2024 and my class is from DKA3D. In my part, I will talk about the first case, the Highland Tower collapse on 1993. First, I will talk about the briefing of the introduction on this building case. The Highland Towers have 12-story blocks constructed between 1975 and 1979 at the western base of a steeply sloped hill, which was later terraced extensively in the starting of 1980s. Each block was respectively called Block 1, the first block that built at the southernmost. For Block 2, it is built at second, the northwest of Block 1, slightly elevated than the other two closer in the hill. And Block 3, it was built last and located at northwest of Block 1 and west of Block 2. Directly behind the three blocks was a rather steep hill with a stream flowing west, if it was allowed to follow its natural course. The attraction of this place was the natural surroundings, with an extensive view of the city of Kuala Lumpur. The Ulu Klang area has been experienced several serious landslides since December 1993, when a block of Highland Towers collapsed, causing a tragedy involving 48 deaths. Next is the causes of the Highland Tower failure. Highland Tower collapse main cause is inadequate drainage. Poor drainage system can lead to some major death, natural disaster which can cause death. From another aspect, design deficiencies are also found. Instability of rail pile foundation can cause a structure to collapse, as the tower itself was not designed for lateral loading. The report has MPAJ 1994 following concluded factors responsible for this landslide Japar 2006. First is the buckling and shearing of rail piles foundation pursued by soil movement. Second is the surface runoff due to improper drainage facility. Third is the cut and fill slopes. Rubble walls around Block 1 show inadequate design. Carrying safety factor is less than 1 and poorly administered construction. Fourth is the slope gradient is suspect to be very steep, and the last one is the causes is no maintained drainage system along with leakage from pipe. In the analysis and design method that used by the Highland Tower building, from my analysis, from the computational analysis done by Prof. Simon and Gue 2006 revealed the facts that high wall has very low safety factor and the design wall would fail at 5 meter very simply, even not including water pressure. The calculated safety factor of all those walls which were at the back of Block 1 is 1.52, even without allowing water forces at the back of the walls. It is also observed under the same study that wall composed of different size of stones with haphazard plaster carrying no drainage blanket over it. A disquieting point was that it had no base directly rest on the ground. Lastly, I will talk about the problem solving recommendation for this building case. The first is the engineers and the architects need to improve the drainage system and also the quality of the retaining wall to avoid floods and landslide whenever a residency is under construction on several dangerous locations or known as unsafe location to people to live there. And the second one is the professionals such as contractors and engineers should be fully experienced in their respective fields. The developer should hire professionals that are certified and licensed. They cannot be conducting a project carelessly. And the last one is the engineers and other professionals of building construction must never take the safety matters lightly. So, stricter enforcement is required to prevent such happenings. Also, the authorities must also play their part. That's all from me about the first case, the Highland Tower collapse. Thank you.
Hello everyone, my name is Romy Crusopovenius and I'm from class DKA3D and my matrix number is 07 DKA 20F 2074. Now I will present about case 3, Ray Foundation failure of a building in Shanghai, China. And for the introduction is in construction industry, it is rare the two buildings are identical to each. A 13-story apartment building collapsed due the foundation failure Saturday morning on June 27, 2009 at Lihuan Road in the Mihang district of Shanghai City. Generally, it is rare the building is collapsed the foundation failure unless it is constructed on expensive soil. Initially, it was thought that at 70-meter section of the flood prevention vulnerability, the Dianpu River might trigger this building. But as the disaster happened, because the block was laid alongside a river and the structure comprised of precast concrete piles. While excavating sub-level parking near the block happened to the other side of the earth up to 10 meter high. Therefore, the weight of the overburdened earth created a pressure which led to a shift in the soil structure and failure of piles. Eventually, rainwater caused the soil erosion around the foundation, which weakened up the foundation and causing them to fail. Generally, it is rare a building is collapsed due to foundation failure unless it constructed on expensive soil. And for the causes of building failure is the Ray foundation failure. A collapse of the building in China was caused by excavated earth on one side and piled up earth and water table on the other side, exerting differential pressure on the piles. When the pile capacity exceeded, the piles fell and the building dropped in en masse, resulting in a Ray foundation failure. It was mainly due to the result of careless excavation very near to the building. For the lesson learned from the failure and avoid such mistake in future. There are four of the point. An excavation for underground was made on the south side to a depth of 4.6 meter without any spot for the earth walls. And second, excavated earth was piled up on the north side to a height of 10 meter. And number 3 is the building experience in uneven lateral pressure from south and north. This was due to the overburden pressure and erosion of soil in a pit adjacent to the building because of heavy heavy rain. And the lastly is the resulted in lateral pressure of 3,000 tons, which was greater than the capacity of the concrete piles. Thus, the building toppled over in the southerly direction. There are 4 analysis and design methods used by the building. First of all, physical risks, improper selection of construction methods and construction company. Ignorance towards the risks during the development work caused the whole building and equipment loss, and one 28 years old worker was killed during the collapse. And number 2, safety risks, improper safety and stability inspection of the site and surrounding buildings. Upper the international building guideline, the factor safety should be more than the adopted one. And number 3, act of God, weather and like rain. And finally, financial risks. The investor spent million in project and had to face a big financial loss. They lost all the money and had to pay the money which were collected from the customer. And there was have 7 of problem solving recommendation. First, site surveys should be properly done, and proper detailed soil testing should be conducted for the site as well as the surrounding area to know the soil profile and soil stability because of the location of the site. And number 2, taking into consideration of the proximity near to the river, proper design and construction method should be followed according to the International Building Standard (IBC) to reduce the risk of failure. And number 3, special materials and equipment should be used for safety purposes. And number 4, advanced foundation technique should be adopted while constructing in weak soil condition. And number 5, careful site inspection should be conducted regularly. And number 6, permission regarding and construction or excavation should be not be given without examining all the aspect of the site condition. And lastly, engineers should precisely consider the geological properties, engineering properties, environmental properties, and etc. before designing any building. And that's all for me. Thank you.
Good evening, my name is Nick Brian Elron. My matrix number is 07DKA20F2050, and I will present about case 5, which is the residential area, ground settlement problems and building cracks assessment at 88 unit houses Taman Muda on lot 6034 Mukim 12, daerah Barat Daya, Penang. The introduction is, the case study is project ground settlement problems and building cracks assessment at 88 unit houses Taman Tunas Muda on lot 6034 Mukim 12, daerah Barat Daya, Penang. This project is carried out in existing residential houses Taman Tunas Muda owned by developers Sri Tunas Harta Sendirian Berhad. The contractor involved in the housing development is also under the owner itself, that is Sri Tunas Sendirian Berhad. The complex of houses was constructed between 1988 and 2002 and consists of 88 units, single-story of terrace houses. The area of the houses is used to be paddy field, and the building is constructed and supported by reinforced concrete piles as the foundation construction. The causes of building failure is first environmental factor. The soil behavior is abnormal soil moisture at the time foundation is poor. Frost, heave and permafrost, decay of organic materials in fields, loss of soil moisture, removal of water which is drained, the vegetation, weather condition and natural hazard. Second is design deficiency. First is error in design concepts, lack of structural redundancy, failure to consider a lot of a combination of loads, deficient connection details. Number 3 is construction fault. First is poor workmanship, under compaction and over compaction. Concrete foundation settlement cracking, procedural deficiencies, poor control material and material deficiencies, called poor joints in concrete foundation. Number 4 is lack of maintenance. Because of the slab or foundation, the movement caused by plumbing leaks, foundation upheaval caused by poor drainage. For the analysis and design method used by the building, the structural damage in the residential area were encountered in 2004 when there were complaints by the occupant to the developer reported the damage appeared in the residence. The damage consists of appeared cracks on the wall, beam, column and apron, and there were ground surface also settled at that time. Based on information derived from the occupant, the developer carried out the site inspection to assess the damage, and then they attempt to fix the problem on site by repair the damage, but the repaired structure cannot resist and later the damage continuing occurred. The groundwater level are susceptible to change in the rainy season. Usually, the groundwater level will increase in the rainy season and decrease in the dry season. It is useful to monitor and record the groundwater level in longer period because of the fluctuation of the groundwater level may be the evidence. Chart below are taken from the two set of reading from the standpipes that the ground is seen to stabilize between 1.38 meter and 1.78 meter below the ground level. High ground water level or unstable water will disturb the characteristic of the soil and reduce the strength of the soil to carry out the load, especially when the type of soil is expensive soil, because this kind of soil is very easy to shrunk in dry condition and expand when high moisture content. The problem solving recommendation is the location of the cracks is as important as their physical appearance. Foundation movement often result in crack at weak points such as window opening and doors. Second is foundation movement tends to distort openings and often causes doors and window to stick. In some cases, the distortion may also affect partition, ceiling, floors, and roof. That's all from me. Thank you.
My name is Ahmad Aklan bin Ahmad, and I will be explaining about case 4 and 5, which is first is case 4, which is stabilizing the Leaning Tower of Pisa. Introduction. The Tower of Pisa, more popularly known as the Leaning Tower of Pisa, is the freestanding bell tower for the Cathedral of Pisa, Italy. It is considered one of the most remarkable architectural structures from medieval Europe and is one of the most popular tourist attractions in Italy. It is one of the 4 buildings that encompass Pisa Cathedral complex known as Campo de Miracoli, or which means Field of Miracles, along with a baptistry, cemetery, and the cathedral itself. Unusually for cathedrals of the period, the tower or campanile is some distance from the main building. The construction of the tower began in 1173, and upon its completion, around 2 centuries later, it was one of the tallest bell towers in Europe. Over the last 800 years, there have been many attempts to correct the structural lean of the tower caused by unstable soil and foundation settlement. Extensive work was done at the end of the 20th century to stabilize the tower, and its lean was reduced to less than 4 degrees, with it currently being more than 5 meters of perpendicular. Cause of building failures about the Leaning Tower of Pisa. It all started in 1173. The original 2 levels of the Tower of Pisa didn't lean, but the structure began to slant when construction moved to the 3rd level and beyond in 1178. Various solutions were tried once the architect took notice of the lean in 1185, determining that the soil is at the chosen site was too unstable to support such a large structure. The construction of the Tower of Pisa stopped for nearly a century because of Pisa's wars with the neighboring city of Florence. Work started again in 1272, and 4 floors were built in an alter angle to the previous level. But the Leaning Tower of Pisa started in the direction of the taller side. In 1284, construction stopped again because Pisa was conquered by Genoa in another war. In 1370, the tower, now 8 stories and 200 feet high, was officially complete. Experts have been divided over whether the lean was an effect designed by other architects or if the lean was a result of structural issues relating to the soil at the base of the tower. However, tests during the 20th century have study of the subsoil revealed an interlayered clay-type material washed by subterranean waters. Analysis and design method used by building. The Tower of Pisa structures was subject to 2 main risks, which is structural failure of the fragile masonry and collapse due to the breaking up of the subsoil around the foundation. A recent possible solution was attempted, but it failed, and it even made the lean worse. Later, scientists and engineers detected that soil extraction was the key to bringing the tool back to stable conditions, which it did by 20 inch to the center. Problem solving recommendation. First is replace the soft soil with adequate soil that will produce the bearing capacity in the second, build a bigger footing and reinforce it with additional steel. Last, use geogrids to provide an effective means for reducing pressure below traffic surface.